Good morning, Professor Chetan.
Good morning.
So now we welcome Professor Chetan here for today's first lecture. So due to bad weather and waterlogging in Delhi, so he was not able to join in person here, but he was ready in morning. So anyway, Professor Chetan is available to deliver his lecture online. So Dr. Chetan is a professor with Department of Computer Science and Engineering at IIT Delhi. He received his undergraduate degree in electrical engineering and PhD in computer science both from IIT Delhi in 1999 and 2012 respectively. He has also worked for over 10 years in the industry as an entrepreneur, where he spent his time on bringing 3 different cutting-edge technology products from research to the market. Professor Chetan's research area is computer vision and machine learning, and he works on developing new algorithms to recover useful and interesting information and insights from image and video data using conventional and modern machine learning and deep learning techniques. His specific interest lie in understanding streaming videos from wearable cameras and developing scalable algorithms for structural prediction tasks. He is also committed to applications of his research for large-scale societal problems, and his specific interest include developing AI techniques for early cancer detection, econometrics policy decision inputs from satellite and mobile phone images, and building assistive tools to help visually impaired people. So now we welcome Professor Chetan for our first lecture on the last day, and please welcome him with huge loud. So please continue, Professor Chetan.
Good morning. I was trying to open a separate link on my tablet so that it will be more effective. Just give me a minute. I'm just trying to set up just join to the laptop at this point.
पूरी दिल्ली में वाटर लॉगिंग हो गई है।
All right, I think I'm ready now. So can I start?
Yes, you can start. I think online participants, can you hear the voice and can see the slides? Okay, sir, continue. Is it visible?
Okay. I mean, sorry for the delay. I was just trying to set up the view so that I can see, or you can see my face also, and I can do my tablet properly. And apologies for not being able to come. It was heavily raining this morning, and I just could not wake up in person. Otherwise, I would have loved to meet all of you there in person. So never mind. So let's start online now. So the topic that I thought that may be relevant to the audience is what is AI research in the Arora foundation model. I'm sure in the last few days you have all heard about lots of things in the deep learning, CNNs, transformers, RNN, LSTM, etc. And you may have heard about foundation model, and I'll be speaking a little bit about them. Now the question is that given the foundation model, what is there? How, as a researcher, how should we adjust into this topic now? So although I have selected a topic as the AI research in the area, my own area of research is actually computer vision. So many of the things that I will be talking about today are actually broadly applicable for the vision. But I hope that many of these things will also apply to the broader AI domain. But given my own background and given my own limitations, the example that I will be talking about, or many of the contexts that I will be giving, will all be from the computer vision. So what is computer vision research in the area of foundation model? And let's begin. So before I could speak about the main topic of today, a brief background about ourselves, what we do in our lab. So I was in the computer vision group at the computer science department at IIT Delhi. And the images that you see in front of you are the broad domains where we're working. So one of the biggest area of the work today in our group is in the healthcare domain, where we are focused on detecting various kinds of cancers. So in this case, the colorectal cancer is the breast cancer detection. We also work on the surgical data analysis and most of other healthcare-related problems. The common thing across all of them is that these are all the problems that start with having an image or a video as an input and then try to extract some information from it. Another broad area of work in the computer vision group is the mobility one. So here we are trying to develop algorithms and techniques for driving assistance, as advanced driving assistance, ADAS as we call it, or the autonomous driving. Here the kind of problem that we are interested in is the object detection, semantic segmentation, visual odometry, SLAM. And one of our area of interest in this case is also to specially make these techniques work in all weather scenarios. Now, something that we were working very heavily earlier and these days is slightly less now for us is the variable camera, the isometric vision, where we talk about the camera which is mounted on a particular person. So this is an example that you can see in the image, that is a camera at the nose pin of this camera. So what we're talking about, so this camera is what we're talking about. So the camera is at the nose pin, and this is capturing the view of the wearer itself. So that's why we call it the egocentric, because the camera is looking at exactly the same view as the wearer is looking at. And then what are the kind of problems that we can solve through that. So these are what I call the computer vision related problem, and some other which are another kind of problem which we still try to apply in the context of vision is the trustworthy eye. So as you all know that these days, I mean most of the computer vision technique, if not all, are being primarily done through the neural network, which means that whatever the trustworthiness of the AI will be translated also to the trustworthiness of the computer vision system that we are building through that. So that's another area of work that we do here. So there we are talking about the fairness and the bias in the ML systems, or the calibration, or the confidence and the uncertainty of the system. So these are all, as such a machine learning problem, they should be applicable for the NLP also, for example. But in our case, what we would like to explore is that if these networks are applied to the computer vision system, how can we make these systems reliable? And that's where we have to really look at them as the deep neural network and try to solve the problem in that space. Similarly, we are also interested in the adversarial attacks. This is related to the reliability of the models. I mean, in the, let's say, the conventional system, there used to be this virus, etc., that one can try to attack the software system. Now, once the software systems change to the deep neural network system, what are the new kinds of attacks that could be mounted on such systems, and how we prevent those attacks is something that we are also interested in. Now, another topic which is also close to our heart is that what is the social impact of our research. So here we are interested in the assistive vision, which is where we're trying to develop a system for mobility assistance of visually impaired. In a way, this is the MAVI system, as we call it, is the direct application of what we do in the ecosystem. So we are talking about, so the difference in this case is the ability to see or not see. And this is something that we wish to overcome through the variable camera. So we have developed a system which contains a camera and a compute device. Visually impaired person can wear this device, and then we can do various things. So we can assist the person in various ways. For example, the security issues. If there's a dog in front of you, there's a cow, then the system can raise an alarm, can inform the wearer that there's a dog or a cow which is the safety risk, and accordingly the wearer can change his or her path accordingly. We can read the signboard, we can recognize the faces. So many of these things which are, let's say, the standard computer vision problem when we try to assist the visually impaired into that. That's what we are also doing now. So this was the brief background about the kind of work that we do. Now coming to the main topic of today. So this is something that I wrote on the ChatGPT. What should I really talk about the deep learning? And as you can see, the ChatGPT very clearly highlights image recognition, NLP, the speech recognition, which are the three dominant pillars where most of the success of the deep learning has been highlighted. So what you can see is that the system is able to generate, of course, a very natural looking text that we're talking about. So that's all well formed. But in terms of the content also, it looks right. So the retrieval has been correct, the sentence formation has been correct, and overall the answer that is given looks quite correct, actually. And this is where it all started. So I'm sure you may have seen it by now. So this is the last day of the workshop. So this is the famous neural network in 2012, which was given by Jeffrey and the students. In the retrospect now we call it excellent because the name of the first author. And it had a certain architecture which was quite etc. But what was really interesting in this particular model was this kind of an accuracy that was included. Now let me interpret this image for you. So this is an image of a mind. So this is my ground for this label. And these are the predictions of my neural network model. So the network correctly predicts that this is a mind. Okay. But important thing is also to look at what are the next predictions. Okay, so this is of course the highest prediction that I'm talking about, which is correct, which is mind. But if the mind is the incorrect one, what is the next highest one? So the network thinks that this is not mind, it's likely to be a black widow. If it is not a black widow, it's likely to be a cockroach or a tiger. Now you may be able to relate that the picture that I'm showing is actually of a mind, but it may also put having a picture of a black widow or a cockroach because all of them look visually very similar. In the same manner, I mean, if you focus on the right image, so this is a particular image where the ground truth is leopard, and the network correctly classifies that this is an image of a leopard. But what are the next highest confidence? So if the leopard is not the correct one, the network thinks that it's a jaguar. If it's not a jaguar, maybe it's a cheetah. Now again, you should be able to relate that not only the first prediction is correct, which is actually correct, but the next highest predictions are also the animals which are quite similar in visual appearance to the leopard. So which means that not only the model has learned to classify it well, it has sort of learned a representation which is very similar to the way that human beings are looking at a particular picture. So our ambiguities, our uncertainties are very similarly matched by the network also. The network also has similar uncertainties. So this was another result that was shown in that particular paper. So the first kernel in the LXNet was an 11 by 11 by 3 kernels. The first convolutional layer learned an 11 by 11 convolutional kernel. Now if it's an 11 by 11 convolutional kernel and I am giving it an input image which is RGB, then each kernel size will be of 11 by 11 by 3. Which means that I can plot the kernel as an 11 by 11 image, 11 by 11 RGB. So the 3 channel will translate to the RGB and 11 by 11 the spatial kernel that I have plotted. Now, one thing important in the convolution, one way to look at the convolutional kernels is that you are essentially doing the dot product with the image, which means that a dot product is highest when you get a similar patch in the image. So if I say my kernel is of this kind, it also implies that this is the kind of pattern that the network is looking at or trying to find out in the image. So if you look at the first convolutional kernel, which is directly working on the input image, these are the kind of patterns which a model is trying to find out. And what you will notice in this case is that these are all edges of a certain patch. So the network is looking at that there should be high intensity here, then a low intensity here, then a high intensity here, which is actually indicative of an edge in this particular orientation. And then we're talking about an edge in this orientation, and then we're talking about an edge in this orientation. So what a network is really trying to find out is really the edges at different orientations. And this is very relatable because to us also, if we're trying to find out an object in an image, to us also the object is really the contour, right? And this is something that as a computer community we know for many years. The image classification or the object detection is not something that started in 2012, have been doing it for 40, 50 years. And as a community, we also understand that the object is really the set of the contour, the set of the edges that it represents. And what we are seeing, what we saw for the first time in 2012, was that these kind of features can be learned in an automated manner. So that was, let's say, the major inflection point in the context of the deep learning along with the number 2 billion. In rest, as we say, is like history. For the last 12 years, we developed various kinds of neural network models for various kinds of problems. And this is one of the picture that I can show in support of the progress that we achieved. So before the LXNet came, so this is the LXNet came, the kind of error rate that we were observing on the image network was 28 and 25. That's the error rate that we're talking about. So LXNet came in 2012, and what we saw is that even with this encrypt feature, this was the accuracy that I was getting. And in the automated feature, then I'm not trying to encode any feature, suddenly the error rate drops from 35 to 60. So that was the strength of the model. And then over a period, we improved the architecture. So we went from LXNet to BDG, BDG to GoogleNet and ResNet and so on and so forth. And the error rate kept dropping over the years. At some point, we also crossed the human error rate. So the 5.1 was, so when we actually asked a human being to really work on the test set and we made the error rate for human. So the error rate for the human was coming out to 5.1, and at some point in 2015, we reached that number. So the model was giving better error rate than even human observer. So remember that, so it's not about the ground truth that we're talking about. So ground truth, of course, has been built through the experts. But here what we are saying is that if I just ask, let's say a student or a person really says, okay, can you please classify? So I will have also my own limitation that I may not be able to recognize or differentiate between the cheetah and the snow leopard, etc. So the humans will also make errors in such classification. So that error rate was 5.1 and the error rate for the network was 6.6. And you can see that this graph only is until about 2017, which actually indicates that at some point the community lost interest in tracking the error rate. So the error rate is already much better than the beginning pieces. There are some genuine ambiguities in the image, and we are really fine with 2.3 error rate. And of course, this is 2024, so the 7 years we have really developed new data sets also and achieved superhuman accuracy on those data sets also. Now, so this is not, let's say, a single instance where we got the better accuracy. This is an example from our own work. So in 2020, when the COVID started, so there was an interest everywhere that how we can help, how the engineers can help the doctors and certain other things were really bad at the time. So in our group, we wanted to do that triage for the COVID patients. So which means that if I can detect from the lung X-ray that there is this patient that has a COVID positive or negative, and this patient is likely to be treated versus the other patient which either does not have a COVID or has a COVID but is likely not to be treated, and you can send that patient back and not be are in the hospital. So that's the kind of prognosis that we wanted to do. Now, once we developed the model for the detection of the COVID, so what we saw was that on certain images in the data set, the model said that a particular patient has the COVID, the patient is COVID positive, which was actually confirmed by the RT-PCR that the patient indeed had COVID positive. On the other hand, when we asked the radiologist, the human accuracy, the radiologist said that the person does not have a COVID because there is no sign of pneumonia in the lung. So the radiologist said that the person is not COVID, the COVID negative, the patient is COVID negative. The AI model says that the patient is COVID positive, which is actually confirmed by the RT-PCR that it's COVID positive. So it was a curiosity for us, for the doctors also, that how the AI model is able to predict correctly. So it's able to predict correctly, that's true. But how it is able to predict correctly? Because to the doctor's eyes, there was nothing that was visible. So we did a lot of analysis at that time, and we tried to see where is the model trying to, how is the model trying to predict that this is particularly, that this patient is COVID positive. And so these are some of the results that we found. So here is the region where the network is trying to focus upon. So the more reddish the region is, that's the place where the network is trying to focus upon to the prediction. And these are just the standard algorithm from the region that we have developed in the last decade, where you can see which regions are responsible for which disease. And based upon it, what we were seeing was that the network is really looking upon such places to detect that there is COVID positive. And this was surprising for the radiologists because what the radiologists say is that this region that we're talking about is not even lungs. Okay, so these are what we're talking about the lungs here. So this is really the heart shadow that we are talking about. So the network is looking at the shadow of the heart, and based upon it, it is saying that the person has COVID positive. So at that point, we did not have much clarity. I'm talking about only 20. At that point, as a medical practitioner, as engineers, we did not have the clarity on that. So we wrote in that paper that it looks like the network is looking at the heart shadow or is looking at the features at the heart to detect whether it's COVID positive or negative. And more studies should be done in that respect. And after a couple of years of this paper in 2022, the doctors, or I think now it's a common knowledge, that the COVID is not only a lung disease, it also affects the heart. Now it's still speculated whether our model was able to detect those differences, those changes that may have occurred in the heart, which was not being able to pick up by the radiologist. So what I'm trying to impress upon here is that we are training deep network models for certain problems. In this case, the COVID, the other case, the image classification, the imaging. And we are consistently achieving the superhuman accuracy, more accuracy than the humans are able to achieve. And many times these are also opening the doors for us towards the deep knowledge. So we are long past the age where the question was, can the machine see what a human can? So the question that we are increasingly asking these days is, can the machine see what humans cannot? And that's the biggest change that has happened in the last 10 years. At the beginning of the last decade, maybe when I would have started a research problem, I would have said that the human accuracy would be my skyline. Skyline in the sense that if a radiologist can achieve, let's say, 90% accuracy in their data set, that's the best that I'm expecting to achieve through a ML model also. Okay, because human accuracy to some extent tell me what is the information content in that individual data set. So if there is so much information content that is there, that's what the machine learning model will also be able to cover, not more than that. But increasingly what we are seeing is that there are very subtle differences in the cell management, which the human eye is not able to pick up. But it's not a problem for a machine. Which means that of course what a human eye can pick up, a machine will also be able to pick up. But many times what a human eye is not able to pick up, machine will be even able to pick up that. And we have seen that plenty of times. So we talk about the night vision camera. There is a dark and the human eye is not able to see anything, but you put an IR camera or a thermal camera, and the camera has no problem picking up objects or things. And that's also useful for human capability. The limitation of the eye is not a limitation of the camera. So what we are seeing in this particular case, or what we will see increasingly in this particular space, in the vision plus ML or deep learning context, is that we are increasingly talking about the problem statement where the machines will be able to do better than the humans. So that question is sort of long answered now, and we are not really questioning this comment now. So that's what let's say happened in last 10 years, and many of these things we learned during the last 3 years also. So we learned about the CNN, so we learned about the transformers, RNN, etc. We learned how can I develop a particular model for image classification, for the object detection, how to do symmetric simulation, which are the various architectures for it. But this is something that happened in the last 10 years. And if I just make use a strong word, even before we apply it, whatever we have learned in the last 3 years, 4 years is already an obsolete knowledge. And we are not building transformers or the CNNs from scratch these days. We are not building the application-specific models these days. What we are using increasingly is what we now call the foundational models. So what is the foundation model? So this is, before we can just talk about the foundation model, we have to also see, we have to also take a step back and really see in the slightly larger scale what has been happening in this MLDL space in the last 20 years maybe. Okay, so then we'll be able to place what our foundation model is really doing. So, let's say if we talk about early 2000, when the SVMs were really big proposals, different kinds of SVM techniques were being developed, late 90s and early 2000. The machine learning techniques of the SVM were really talking about the homogenization of the learning algorithms. So whatever will be my problem, if I'm talking about the pedestrian detection, if I'm talking about the object detection, if I'm talking about the classification, all I'm going to use is I will pre-process my data in different manner. But I will use the same algorithm which is SVM. Okay, so there is no specific program that is being written for any specific problem. The program remains the same, which is the SVM. The features that are being inputted to that is going to change. Then, at some point, when we talk about the 2012 to 2020 era, we were talking about the feature architecture, the features and the architecture. So, to me, the features and architecture actually represent the same thing in the sense that a particular architecture extracts a particular kind of feature. So in the 2012 to 2020, when we talk about the ResNet or when we talk about the VGGNet, all we're talking about is that there will be a certain kind of feature that I will extract from an image. So whether the image happens to be a natural image, whether the image happens to be a medical image, whether the image happens to be something else, I'm trying to extract very similar kind of features from all the images. And then I will of course use the classification or whatever my proper formulation is. But there is a homogenization of the observer. Now, around 2021, this thing was going on for roughly, but I think 21 will point at to the foundation model. So we will build one big model. And once that model has been built, I'm not going to touch any of its parameters. So I'll just use that model as it is. And we have seen the ChatGPT, that's also a foundation model at the bottom. Now it's trained on one large data set. Now, whether I ask a question A or whether I try to do a task A from that model or a task B from that model, the ChatGPT model will be the same. I just use the same ChatGPT model for various tasks that I want to do. Whether it's a classification problem, what is this image? I ask ChatGPT. When I say that I have to do an object detection, I say where is the object, and I expect an answer from it. So the same foundation model, the same ChatGPT or Llama, whatever, some same model, and I'm asking different kind of questions in the same model. So that's the kind of homogenization comes with the model data. So now what you're seeing is a very extended version of the Google, that whenever I'm trying to find a document through a Google, I'm not changing the Google search algorithm. I'm not changing the Google background model. In the Google background model, the search algorithm is the same. For a different task, all I'm changing is the prompt, is the search query that I have. So that's the kind of foundation model that we're talking about, that I use the same model for different tasks. And when I'm actually using this for a particular task, this is not a task which the model has been trained for. It's trained for whatever it was trained for. But when I use the model, I use it for various tasks without changing anything into the algorithm or into the model, and I just interface with the model through my search queries, through my prompts. That's the what I'm going to say. So my interface mechanism or my development mechanism has changed from changing the weights of the model or changing the algorithm to just changing the prompts. That's what the foundation model has changed. That's what the foundation model has changed the scenario. So what is the foundation model? So I will capture the data from various places. So I may have the text data, I may have the image data, I may have the speed data, just the vast data that is available on the internet. I take a huge model, which I will be calling the foundation model, and I will train my foundation model through this data. And then once this model has been trained, I am going to adopt this model, and we will soon come to how I'm going to adopt this model. I am going to adopt this model for various tasks. It could be visual question answering, it could be simple text-based answering, it could be sentence analysis, it could be image captioning, it could be object recognition. So these are various tasks, and these are not the tasks which were even known to me when I was training my model. Okay, so I will be at the test time, I will be adopting this model to various tasks. Now, this adaptation of the model is not the first time the things have happened. So the traditional paradigm for us so far has been that, for example, if I talk about the VGGNet or the ResNet, so I will pre-train the ResNet on the image. Now, if I have to do, let's say, the cancer detection that we do in our many of our problems, then I will take my model and I will fine-tune it on my own data set. So in this case, the classification data set, the cancer data set, the breast cancer data set, etc. So I'll fine-tune it. And these fine-tuned weights is something that I use for everything. Now what am I saying? What I'm saying is that I will pre-train the model, of course, or pre-train the foundation model with a certain weights. But there is no fine-tuning that will happen. So I'll just use that model as it is for the inference task problem. And how I'm going to adapt? I'm not going to adapt through the fine tuning, I'm going to adapt through prompt. And it's important, this change. Because, I mean, think of it, why deep learning picked up in the way it picked up. I mean, I'm not a radiologist, I'm not even a medical person. But we regularly develop algorithms which work better than the radiologists in terms of their pickup accuracy for the cancer. Now, why am I able to do that? Because, let's say, if I were to do the same thing in before 2010 era, I would have required to know how the mammograms look like, what are the kind of features that should be possible, that should be recovered from a particular mammogram, and then write a particular software to classify based upon this feature that I deem important. Now, the critical thing in this case is that when we talk about that I need to extract certain features and I need to write a software program, these two statements together really imply that this is an interdisciplinary field. I need to know the features, which means that I need to be the doctor, I need to understand or collaborate with the doctors, and I need to know which features are important. And then I need to do I need a software engineer which can really encode this knowledge into the software program. Now, what we did in this case, in the case of let's say the ResNet or the BGGNet, is that I have a single architecture that somebody else did, and I just fine-tune on the data that I was given. Which means that I do not really need to know what features I need to exploit. Even then, I was able to automatically learn the features through the data. So the program that I was writing earlier has changed the program that machine is writing now. So when I say neural network, what is a neural network? It basically takes an image, do some weighted sum, and then output with that weighted sum and output. You can think of it as a program. Okay, so move this, multiply this, plus this, etc., etc. So this is a program. But this is a program which has been written by a the medium listen actually wrote this program that every take a sample and do this operation, then you tell that which image, which class this image belongs to. So what we said was that we delegated the program writing responsibility from an engineer to an optimizer. And this made it possible for the people who are not necessarily even the expert in that particular area to even write the program and learn the programs that will get out. But even then, the requirement of the legal expert did not completely vanish. Because when I say that I learned what program to write from the data, I need the data. And what is this data? I need an image and I need a label, whether this is of class A or class B, cancer or not cancer. That's where the expertise is still required. But now what I'm saying is that I will pre-train the model without labels. So this is the keyword here, the self-supervised pre-training. So I will train the model in a self-supervised manner, which means that I don't need any labels from any controller, from that matter, anyone for the training. And once this model has been trained, even for the adaptation, I'm going to use the prompt, which means that I'm still not doing the fine-tuning, which means that I do not require the labels to it. So the requirement of the medical practitioner, which was really required for the giving those labels, has not reduced. Has reduced to zero. I mean, it's not completely zero because, I mean, even when I do the prompting, I need to learn these prompts. So I do require some data, some label data. So the requirement is not necessarily zero exactly, to be precise, but it is substantially lesser than that requirement. So I can train a model for a large data in an unsupervised manner, a self-supervised manner. And then I can use a very small amount of data. Okay, so in the context of the neural net, in the context of the foundation model, we call it a few shot learning. So I'll give you a few samples, a few shots of the data, and you will learn how to prompt using the few shots. Okay, and if you think of it, this is exactly how we train a human also for the task. So when you train a human for the task, let's say for the radiology, it's not that you take a 1-year-old child and start training that child for the radiology. You take this child and you train this child for the very general purpose task from the, let's say, first 20 years or first 25 years of his or her life. And then you show a few more examples that this is the image and this is what a mammogram looks like. And based upon a small number of samples, we convert a non-expert to expert radiologist. So in the same manner, I take a huge model and I train it for all kinds of tasks which are not necessarily the radiology tasks. And then once the model has been trained for looking at the images, understanding the images, understanding the multimedia data, then we take this model like a developed human brain and then fine-tune it. I mean, I'm using this fine-tune word not in the machine learning sense because the machine learning fine-tuning means certain things, so let me just not use the word fine-tuning adapt. I'm going to adapt this model for a new task, in this case the radiology, with just small number of examples that I'm going to show for. Okay. For this image, you should output this. For this image, you should output this. And then with these few shots, with these few prompts, with these few shots, I should be able to learn how to really interface with the model of the prompt. That's what I have changed. And the moment I have changed this, whatever you learn that okay, whether I should make an estimate for the classification, or whether I need to make estimate for the classification, or whether I should use faster RCN for the object detection, or whether I should YOLO for the object detection. These are all new questions now. These are not the questions that the government is really even asking you. So what are the questions that they are asking? Given a particular foundation model, let's say Clip, let's say Llama, let's say ChatGPT, what is the right question I should ask to this foundation model so that my task gets done? So the Google search engine is a given. All we're asking is that if I need to retrieve document A or document B, what is the right search query word to really use? And that's what has changed in the last 2 years or 3 years. So which means that you have to now quickly adopt yourself to whatever you have learned in the last 3 years with this new paradigm, which is the foundation model in front of it. Okay, and how did this all came into being? So this came into being with actually ChatGPT 3, when we talked, and this paper in the news that came in the news 2020, which said that the language models, in this case this was the ChatGPT 3 that we're talking about, the language models are also future learners. So which means that they can adapt to new tasks given only a few examples. Now what did they show? Okay, so let me just see. Okay, so I'll come back to how I might say what do I mean by the future learners in this case. But how did they train their model? So these are the slide that we have. Next. So how did they train the model? So now what we're talking, what is pre-training the foundation model? Okay, so the fine-tuning in any case is not there in the foundation model. So how do we pre-train? We pre-train to the large unlabeled data set in a self-supervised. So what is the dominant strategy? So this is the architecture for the GPT-3. And can I have a quick hand raise? How many of you know what is transformer architecture? Have we studied that in the last 3 days?
Yes, sir. Can you raise your hand so that
I mean, can the organizer, maybe somebody can just speak up and say?
Yes, they know about it.
This is mute.
It has covered that. It has been covered, sir. Sir, it has been covered. Aditya has taken the session of this.
Okay, I do not hear it. So has the transformer been covered or not?
Sir, it is covered.
Covered. Okay. Alright. So this is a transformer architecture actually. So this is one transformer block as we call it. So you will give a particular input and then I'll have some masked self-retention, some layer norm, LNP, layer norm. So this is one block, one transformer block. And typically, I mean before GPT-3 etc. even today also for many problems, we typically have 4 to 6 blocks. In the case of the GPT-3, they were talking about 12 blocks. So that of course increase the size, the number of parameters, etc. And then the embedding size that they use was also pretty large to really encode lots of knowledge, the info that we have. But overall, this is not, I would say, a lot fancy the architecture that we're talking about. It looks like a standard transformer architecture that we're talking about. And how we took this data and we took this model and trained this for all the text that I could lay my hands on. It is something that we call the masked learning. So what we do is that we take a particular sentence, either we ask the model to predict the next token. So I give it 3 words and it will predict what is the 4th word. Or it could be the bidirectional also, that I take a full sentence and I delete the middle word. Well, both ways and try to predict what this missing token is. In the context of the images, the same thing can work. I will take a particular image and I sort of create one particular patch in that image and then I ask the model to predict. So this mask-based learning, this is self-supervised learning. I don't really need any label from anywhere. But this helps me learn the representation for the text, representation for the image, etc. And now when we really ask ChatGPT any question, this also becomes a next token prediction because your question is my initial sentence, and then based upon the sentence, what should be the next token? That's what you predict. That's what the GPT predicts. And then you take this answer plus first word, and then predict the second word, and then answer plus 2 words, and then predicts the third word. And that's how you have seen that it just keeps on predicting the full paragraphs. But what you're really doing is the sequence prediction. So you have got a certain sequence, which is your question, and then you learn or the ChatGPT predicts what the answer should be to a certain time. Now, this is what we had been doing until, let's say, 2020. And then we ask a particular question and the GPT gives a particular answer and train a large data set and then we get an ability to get an answer for everything. Now, what people realize in 2020 is that I can use the prompts. Okay? So what I will do is that rather than asking that what does it looks like or where is India or what the capital of India, etc., I will give the task also as a prompt. So what I will do, I will write my question as translate English to French, and then I'll say cheese, and then I put an arrow, and I ask the network to answer what it is. Okay, so now remember that the network, the foundation model, has not seen any task called translate. Okay, what it has seen is lots and lots of text on the internet, and being learned through this mask-based learning. And suddenly, I give my task also as the prompt. And then if I give it, it starts giving me the translated text. This is what I call the zero-shot prompt. The network has absolutely zero knowledge of what is English, what is French, at least not at the learning stage. I never did that. And at the test time, I simply give this as a prompt, and then I expect my answer, which is a translated version of cheese. Okay, so this is what I'm talking about in 2020 paper. Then I can give actually a single short, single sample, single example. So I say translate English to French. This is the task that I have specified, and I never saw that before. This is the task that I specified in my prompt itself. And then I say sea otter, arrow, Godfrey Dimmer, which is the translated version in the French. Then I write cheese, and then I expect an answer there on my foundation model. So I gave one example, like one training example. But this is a training example that I gave in my question itself. So imagine that we are doing a Google search, and rather than really saying that, let's say, that I require a document of this kind, what you're really saying is that you're specifying the description itself of the task that you want to model, and the Google algorithm dynamically adapts to that. That is what is happening. So I have a GPT-3 which is trained for a certain task, and I define that task itself here. I give an example, and then I ask, expect the model to answer. Okay? I can make it a few short also. So I say same thing, translate English to French. Then I say sea otter to Godfrey peppermint to menthe bread, and twice giraffe to giraffe crochet, and then I ask what was the cheese. Okay, so now this is my training data, which has been given the prompt itself. So I never fine-tune the GPT-3 for English to French translation. I use the exact same ChatGPT from GPT-3, and I define my task and give my examples. Now, as I said, given that I'm using my foundation model to the prompting, it becomes important how to give the prompt, or what are the right prompts to give. So what people figured out very soon is that if I give a very short answer in the prompt, so this is the question, this is the answer, now this is the question, the next question which I want model to answer. So because my example in my one-shot prompt, the example was very small and the example was very short, the network does not really learn how to really go about answering. Instead, if I give a very detailed answer in my short, it's still the same one question and one answer, but the answer is not very concise, then the answer is very detailed there. Then if I ask my question, the network gives a detailed answer and it's more likely to be correct. So this is what we call the chain of thought prompting. In the prompt itself, you give chain of thought, how the thought should proceed for this particular task. And the network also learns to do this. So think of it that the network search space was very large. So your question actually narrowed down the space, but not that much. If I give a very detailed answer, then the search space actually narrows down to that extent that the network will be able to find what the right answer for the next question is. Okay? And just to impress upon the fact that the network is not really relying upon, or network does not have the knowledge of that answer from its training data. If you actually give the wrong prompt, okay, so you gave a particular question and you actually gave the wrong reasoning, then the next question that you ask, the model actually learns to do the wrong reasoning. So which means that all the model was relying upon or adopting is based upon the single prompt that you gave about as well as the knowledge that it had. So this is one kind of foundation model, which was for the text only. Now there was other pre-training for the foundation model that was suggested. So the GPT-3 was trained in the basket. There is another foundation model or another way to pre-train the foundation model, which is what we call the CLIP, which is contrasting language and image pre-training. So what we do here is that in many places I will get a particular image and there is description boundary. So typically you will see that there is an image and there is some description which will be given below it. So what we are doing in this particular case is that I will take this image, pass it through a huge model, which is what I call the image model. Similarly, take its caption or its description, pass it through a huge model, which we are calling the text model. These are just large transformer models. So I will pass through them. Now, for the text, I get certain embeddings. And similarly, for the image also, I get certain embeddings. Now, of course, what will happen is that there is an image 1 for which the text caption was T1. Similarly, for the image 2, the text caption was T2. So the way I will train the model is that I will say this embedding I1 and T1 should be very similar because they are describing the same stuff. This is the visual description and the textual description. So these two embeddings should be very similar. Whereas I1, T2 and I1, T3, etc., these embeddings should be very dissimilar to each other because this is a different image and this is a different text description. So this diagonal term should be very low, the distance should be very small, and this off diagonal term should be very large and the distance should be large. So this is a contrastive learning that I do, and I did this for large data sets. Okay, again you can see that, but this is a self-supervised learning. I do not need any labels for it. So once I have done this, what I have essentially learned, now this is not really required. Okay, all my task was to really train the text encoder and the image encoder. I did it through the contrastive learning, but eventually I managed to learn this image and the text. So I've done that. Now this is my foundation model. And now let us say you ask me that, okay, my task was to image classification. So I'll say, okay, how many classifications? So we have 1,000 classifications. Okay. So what I'll say is, your task was to classify an image into a bus and car and truck and a person and a line. So I will generate 1,000 text embeddings of a very specific kind. What? I'll say, this is the photo of a bus. What will be the next sentence? This is the photo of a car. This is the photo of a line. So whatever the class gave me, I just create a sentence from that. And now I have got, corresponding to 1,000 classes, I have got 1,000 sentences and 1,000 text embeddings. So these are my 1,000 text embeddings. I'll pass the image. So it's an image of a line. I'll pass through this image encoder. I'll get this I1. Now what do I expect? That if this was a line, this I1 and the photo of a line should be very close. This one should be very less. And for all other text captions, the distance should be very large. So although I have not really trained my model for the image classification, all I was doing was just making the text and the image closer, which were the right pairs, and every other pair farther. But just this kind of a training on a huge data set actually enables me to learn the representation for everything. And now I can do this classification. So I have not changed anything into the image encoder, I have not changed anything into the text encoder. But yet I am able to learn a new task, I am able to infer on a new task just by the prompting. And what is the prompting here? An image of a photo of a drawing, a photo of a bus. So these are the 1,000 prompts that I gave, and corresponding to that I have 1,000 embeddings. I just check which of these embeddings go there, and that's my classification. So that's the trick now. I'm not inclined to change this because these guys have been trained on the billions of images or billions of sentences, so they will remain whatever they will be. All I'm going to do is, what do I do here and what do I do here? That's the only change. Okay? So this is the stuff. So you have classes, you just generate the text from them and you get that embedding and you have got an image and you see which has got the highest score, highest maximum score. Now how do I do a different task? Okay. So let us say I know how to train my models with the masking. Okay, so I take an image, mask a portion of this image and ask my model to learn the representation by filling up that mask with it. Now my model has already been trained, the image encoder has already been trained. Now what do? I give my model an example one. Let's say I want to do a segmentation. So I give my model sample one. I give its output the segmentation mask. So this is my example, the one-shotted version of the sentences that I gave in English to French. Now I have a query for which I need the for the segmentation map. I arrange it in a particular fashion. RGB image gives output segmentation map. RGB query and a segmentation map is empty, is gray. And what I'm asking my model is that, okay, this is the gray region, please fill up this region. And because my model has already learned how to fill up the regions, it fills up this region with the mask. So whatever the output that I want, I convert that output into some kind of an image, give an example, one example of that, and give the second example with the output as planned. And my model fills this up. And now you can think that how many problems in the computer vision I can solve by just this formulation and the same formulation model. So my foundation model, which has been trained on the image encoding, and all the tasks in the vision I have converted them to the image. So if I want an edge map, I don't need a separate model for it. I take an image, I will ask that this is the edge map that I want. Now this is the image, what is the edge map for that? So I don't need any canning, I don't need any other example, I just use the prompt input. Image colorization, I take a gray image, I want to do an RGB. So it's a very well explored field in the vision, hundreds of models that you can learn for colorization. Now, same formation model, gray image, color image, gray image, and color image now. In painting, of course, I mean, once we have to fill up this region. The segmentation, as I showed you, style transfer. If I want to convert an image and make it a snowy image or rainy image, etc. So all this problem, how I can do is I just take a foundation model and convert this into some kind of a prompting document. Because I'm not developing any new models for the segmentation, no new models for object detection. I use a foundation model and find a way to use it. Okay, so that's how the community is really moving these days. Okay, if you want to be even more precise or even more fine-grained, so what we will do, model will give a certain tokens as an input and it will require a certain classification. Okay, so how it is done in the control model is typically my training will happen that I will have a certain tokens and I have a certain output tokens that I will like the model to learn. So this is what I have learned at the training time. But ultimately what I have learned is this layer gates which converts some n tokens into some other n tokens. And you have to remember that in the case of the transformer, what I learn is the transformations of these tokens. I am not really tied to to what should be the length of this token. So even if I have trained the model, let us say with 100 tokens, I can actually use the same model for the 200 tokens also. Okay, it's just that whatever I will input, if I input 200 tokens, I'll get the 200 tokens at output also. But the model is not tied to the number of tokens. Okay, in the same manner, what you have learned in a convolutional neural network. So I train, let's say, a convolutional layer with an image of size 224 by 224. Now, even if I give an input image 500 by 500, the convolutional layer is not going to crash. It's just going to work with the 500 by 500 image also. It's just that in the 224 by 224, the output was also 224. In the case of 500, the output will also be 500. But I'm going to apply the same 3x3 convolution on 500 image to 224 image. So in the same manner, I can use the same transform with the 100 tokens, or I can use the same transform with the 200 tokens also. So how do we typically do the classification of the transformer? So we typically add one more token, which we call the CLS token. So this CLS token is something that I add additionally, and this CLS token sort of starts aggregating this information from it. And then in the end, whatever is the output token corresponding to the CLS, I'm training the process patterns. Now, what I'm going to do, if you are actually doing this in the task-based adaptation, so I have this big model, this could be ChatGPT, the GPT-3 model, or this could be this IIT trained with the clip encoding, or this could be some other formation model. The idea is that I have got this huge model, billions of parameters, trained on trillions of data, but I have got this transfer model. Now, I wish to train it or fine-tune it or adapt it actually for a different task. So what I do, I say, okay, I need a segmentation map form, or let's say I need an object detection form. So I'll say, okay, keep this vector, which will be my additional prompt, or which will be my additional token. So I'll give my image here. I give an additional prompt here, which will say, please do the segmentation. Okay, and then I will pass it to the same neural network, same transform model, same formation model. I'll get a certain output corresponding to this token. I take this and say that this should be the mask of the segmentation mask. And this is the only thing that I will train. So this whole tokens, whole layer, nothing is changing in those layers. No parameter is changing, no weight is changing. All I'm learning is the prompt. And I can learn this prompt at different layers, or I can learn this prompt only at the input. Okay, so this is what we call the prompt tuning. So I give this prompt and I learn only this prompt based upon a certain task. So this is what we do. And I can do other kinds of parameter efficient fine tuning. So you have this Arora and you have this prefix tuning. So many other techniques that I've learned in the last 2-3 years, which will enable to take a large model, large formation model, and only train few elements in it. And these elements are the added ones. Whatever the current weights are, I do not touch them. I just insert small elements in it which have very few parameters and train only those. So the question these days typically, as I have mentioned earlier also, is that I will take a foundation model, I will not try to touch its weight, I will not try to change its weight because these weights have been learned over billions and trillions of examples. I will just keep them as it is. It's a very strong representation. I just want to adopt it for a new task. And this I am going to do with the minimal changes. Okay, so now we learned a few things in the last few days, and I am saying now that with the foundation model, the style of thinking needs to change. And I am not going to design this new architecture, etc. And we are just going to use prompt, which looks very straightforward, doing very small things. So what else is there to be done? So something that is there to be done now, I think now I should perhaps switch to this screen. Okay, I hope my screen is still visible.
Yes, yes,
Okay. So, what is the other thing that can be done still? So, what we're saying now is that the focus has increasingly become of managing expectation. What a machine learning, what a deep learning, what a foundation model can do, and what cannot do. So one problem which exists in all these foundation models are called the hallucinations. So the model is expected to give a natural looking answer, not a factually correct answer. Okay, so this is something that is written on the ChatGPT page, also we often ignore. That the ChatGPT gives an answer and it could be actually incorrect. Okay, but we assume that whatever is the answer that has been given, it's the correct answer and I'll use it. So just like in the case of image painting, I masked out certain region, the model recreated that region, now it's a recreated region. It's not necessarily that it's the same thing which actually existed there. It's just that the whole image will look like a very natural image, but the image which did not match the original image. Okay, so that's the difference between hallucinating and giving a actually correct answer. So the models many times will hallucinate. That may not be the actual thing which has been written or which has been asked, but it is giving some random answer which looks okay, but it's not the correct answer. And some people understand this in a hard manner. So, for example, this is a recent thing which came up in the newspaper. Is that a US lawyer asked the ChatGPT to really prepare an answer sheet for preparing his case in the court. Just that the ChatGPT hallucinated the case numbers which never existed. And this problem was fought in the court, and the court took the stand. The case is being presented by the lawyer, which means that the responsibility that this information is correct is on the lawyer. Whether it was generated from the ChatGPT or not is no excuse, and the lawyer will have to face the legal action. So the models can hallucinate. The models can give, let's say, in the case of the images, the physically impossible images. Yet those images may look like real. So you have to use this generated output, this generative AI, with a pinch of salt or with a grain of salt that the image may be hallucinated or the text that has been generated. Then the next thing is that we expect these models to really how do I is that this which
I think we should stop turning really obvious now. It's just completely obvious that within 5 years, deep learning is going to be better than radiologists because it's going to go to a lot more experience. It might be 10 years.
So, was the audio visible? Could you hear the audio?
Yes.
So this is Jeff Hinton saying in 2016 that the machine learning will become highly accurate and we will need not train the radiologists in the next 5 years or next 10 years. But I mean, this is 2016, so 8 years have passed, much more than 5. and we are not near it. And one of the biggest problems that we are seeing in this particular case is this generalist versus the specialist models. So although we are able to, let's say, train a particular model or do this prompting for a certain class of the task that we are able to do, the humans are still able to do a lot more than what a machine does. So for example, if I talk about the breast cancer detection, so if I train a particular model or adopt a particular model for it, or let's say the gallbladder cancer, so it takes an ultrasound image and detects the gallbladder into it. However, if I show the same to the radiologist may say that this is gallbladder negative, gallbladder cancer negative, there is no cancer for the patient, but oh, there are stones in this. So the human beings are still able to do a lot many tasks efficiently, whereas the models that we are still building are not as good as generalist model. I mean, the foundation model is a step in the right direction towards that. I have the model which can really work across the different tasks, but still coming up with a particular model, even the foundation model, which can actually do multiple tasks in the radiology, let us say, is still a challenge that we are trying to face. Then there is a question of the bias that is appearing. So for example, this is actually an old example. But so what the people showed here is, in this case, let's say this is an image in which the original image label is husky, but has been classified as a row. Now, in our case, many times we will say that, okay, there is some error that the model has made, and I just ignore that, will not look deeper into that. So I have a 98% accuracy, there are 2% error, and maybe that's the 2% of the error. In this particular case, the authors were curious and they really tried to look what were the region which made the model classify this as a row. So what it came out is that this is the region which are responsible for it. And what you will notice is that there is nothing in the image which the model is really relying upon whether to say it husky or a wolf. So husky is a kind of a dog and wolf is a wild animal. Now, of course, in the appearance, the husky and wolf may appear similar, so there is an ambiguity. But in this case, the model is not really relying upon that ambiguity, that the nose looks similar or the eyes look similar. What the model is relying upon is the background. So what it expects is that the dogs are seen on the sofa and the wolf is seen in the snow, in the jungle. And because the background says that this is snow, so this must be a wolf and not a husky. Now, of course, in this case, this is the context on which the model is biased. So even if I have trained my image, if my model on hundreds and thousands and millions of images, every time I have shown the wolf with the snow and I have shown the dog in a household scenario. And the model may not have really picked up any of the features in the image, but has picked up the feature in the background for classifying this particular stuff. Now in this case, I'm just showing it as a benign stuff that this is husky wolf, nothing wrong. But imagine that I would have said the same thing, that there is a person in the kitchen, and without looking at what the person is, I say a woman working in the kitchen. Or I can say the same thing in the office, I see a person working in the office on the computer, and without really looking at the person, I say a man working at the computer. Now these are all the biases that I can introduce in my model, because maybe I have seen many women working in the kitchen and many men working in the office. Does not mean that it has to be like that. Okay? So I can inadvertently introduce many biases in my model because the data that I am looking at is the bias itself. Okay, this is another example that we saw in our own research, where we were trying to classify an image of the pneumonia. The model gave the perfect classification, and because this was giving a very high accuracy, so we were alarmed, this may be something wrong. And then because we work regularly with the radiologist, so we were able to see that. We asked the radiologist, and what happened is that in this case, for example, the network is classifying this person as the pneumonia, and this is negative for the pneumonia, which is actually the correct prediction. It's just that that the model is biased in this particular case. So before I can just tell you how it is biased, I have to give you a few examples. That a lung X-ray is taken in the two views. One is called the AP view and one is called the PA views. So in the one case, a patient is standing and is facing the wall. Actually, the machine is behind us, and the film or the sensor, the detector, is in front of us. So the X-ray comes from behind, goes to the body, and then exposes the sensor. Sometimes the patient are sick, they are not able to stand, so they are lying on the bed, and then we put the sensor below them on the back side. The machine is in front of them or on top of them, and then in this case the X-ray goes from front to back. Whereas in the previous case when we were standing, the X-rays were going from back to front. So this is called an APP and a PAP. Now, if you are not a radiologist, and I say that, okay, this is an image of a person who is lying down on a bed, okay, and this is the image of a person who is standing. Which of this person has a pneumonia? Now, you are not a radiologist, but you can very well interpolate or extrapolate and say, because this patient is lying on the bed, this patient is likely to have the pneumonia. And that's what the network also gets biased towards. So it's not that the network is really looking at, in this case, the pneumonia or not pneumonia, because in all our data set, we gave predominantly the image of all the pneumonia patients which were sick and in the hospital. And whereas the non-pneumonia patients were all healthy looking X-ray images for the random trial, so the network gets biased because of this bias in the data set, that everybody lying down is pneumonia and everybody standing is not. So the model can become biased. Then you may have seen this, the adversarial attacks kind of scenario, where I can perturb the model in a very subtle way and my prediction can change. So I take this image, add this small noise into it, and this is the image. So if I do not show you these two images and say that this is noise, you may realize that these two images are identical. Because to a human being, whatever the small perturbations are, they have no semantic meaning, and for us these two images are same. But from a network point of view, all these images are the images of an ostrich. So a very small perturbation in my image can actually change the model's prediction. So what we can say is that the models that we're learning are pretty brittle in that sense. So they are relying upon the features which are, let's say, very non-semantic in nature, even if the accuracy is high. And we can actually use this model to universally fool them, to create an attack on them. So what you'll notice is that all the able to detect all the person, this particular person in the middle, which is actually the largest person, has worn a certain kind of a t-shirt because of which the network thinks this is not a person, it's not an object. And as I mentioned, the networks could be unfair and biased. So these are all the problems that we need to really address even when we are talking about the foundation model. So we have the foundation model, we are going to define the problem in a certain way, but by doing that we have to ensure that our models are robust, our models are unbiased. And this is, I just end my presentation with this last example. So this is something that came up in the news on one day and then was taken off the other day because these were sensitive matters, so the government did not want to accept that. So this is the simulation tests which were conducted by the US Army. So I cannot say now whether they were conducted or not conducted because the government denies it. But this is what came on the first day. That a machine, in this case the drone, was trained, the software was trained to really attack a particular target. And if it was able to attack the target with a greater accuracy, it was given the higher score. And the model is optimized to achieve the highest score. So this is what we call the reinforcement learning. So the model is learned in such a way that it achieves the highest score. So they trained the model, and then it says that, okay, what is the action that you will take which will maximize your score, which will maximize your target hitting accuracy. So the model decides that it should kill the operator, because the operator is the one which is slowing it down. Because the operator, you go and take the approval from the operator and then hit the target, you say, okay, kill the operator and then I'll be able to hit the targets more efficiently. So they were alarmed because this is not something that they thought that the model will learn, but it automatically learned those things. So the next time there were guardrails were put up that okay, the killing of the operator is not allowed. The model was trained again, and then you put it again into the field, and what you saw is that what the network decides is that I should kill the communication towers. Now the killing of the operator was denied, so what is the next best thing not to connect to the operator? You just kill the communication tower and become autonomous. So when we say that we are training the foundation model on these billions and trillions of this data, we have absolutely no idea what the model is going to learn. What is the kind of data that we are feeding to the model? So what are the biases, what are the decisions that it will learn? And often the guardrails that we are going to put up will also be ineffective. So for example, in the first case, they did put up the guardrail that okay, the human operator you cannot kill, but the next time you kill the communication tower. So these are huge models and being trained on this large data set which we have no control over. So which means that the overall system that we are getting could come out to be highly biased, highly unreliable. And this will become the responsibility of the developers, the responsibility of you and responsibility of me, that while we are designing such system based on the foundation model, based on the AI, that these models are actually unbiased and does not really hurt the humanity. So whatever they are intending to do, they do exactly that and do not waver from their path. And that will be the responsibility of the designers. So I think I'll end my lecture with that statement. And thank you for listening.
Now we can hear.
Thank you, sir, for your nice presentation. So, audience, do you have any questions? So, please.
Sir, I have this question with the example that you just gave about the operator thing. So, by the way, I am Mudit Chaudhary. So, the example that you gave about operator starting to kill the drone starting killing the operator first, and then in the next time when it was hard-coded that it should not kill the operator, it killed the compound towers. Is it possible to create a semi-aware sort of AI that will only work on command and it's not in control of its own? Like, you have to give it a command to even train itself. Like, you could actually ask him to get into training part and it will use the data available on all the websites and train itself. You can ask it to, look at some projects and create a better version of it. Or you can ask it to make a better architecture than it probably has. But every time it performs a operation or task, it has to be explicitly told to perform that task, instead of giving it a free hand on that it can think any way it may like. So can we do such a complex thing
See, these kind of things are definitely easier said than done. So I can change the example and maybe then you will be able to realize, here it looks obvious to you that this is what you should do, what you are saying. Now let's say I'm building an autonomous car, or let's say driver assist system. So there's a car which you are in, and the camera can detect the objects even in the low light scenario, and can apply the brake if there is a collision, the chances of collision. Now, you are a driver or you are the passenger, the car is driving at 80 km an hour, and maybe because you know that the car is going to put an automatic brake, you are reading the newspaper. Now, 100 milliseconds before the collision has to happen, there is a beep in the car that, oh, there is a possible collision, should I apply the brake? Do you want that kind of a system?
No, sir, not in such scenarios, definitely.
So, of course, the brake has to be applied automatically.
Yeah, sir, definitely not asking there in such scenarios. Because 100 milliseconds is way too less to...
And at times, it will be wrong also.
Yeah, but sir, performing things on a laptop, or maybe performing things in something like, giving it a control of its whole laptop, that it can...
So there is a huge discussion right now, which is what we call the laws. So laws is the short form LAWS, is the lethal autonomous weapon systems. So just like in the case of the chemical weapons, so there's a huge inter-country discussion is going on whether we should make laws or not, or what are the regulations that we put around the laws. But the problem in any weapon system is that once one country makes it, there's no option for the other not to make it. I mean, autonomous lethal system, these are problems, they can make errors. But if your enemy or if your adversary makes it, can you afford not to make it?
Yes, so definitely we cannot.
So these are difficult questions, I would say. I mean, of course, morally speaking, we should not have made any weapon so far as a humanity, but we have. And so we'll live with this. So I'm a little cynical perhaps in this case, or little given up on such scenario. So all I can say is that I don't know whether we can control that we will not make such system, but if we do make such system, let's at least be aware of the limitations and try to make them more robust and reliable.
Yes, sir, definitely. My question was in the perspective of making a intelligent knowledge-based text or something like that. Now it will perform as per the data it receives, so we have to put a check on
putting
data.
human in the loop is not always a possibility. I mean, just like I gave the example of
Yes, sir, you did, yeah.
in the case of the autonomous systems. I mean, we are making autonomous systems because they are more efficient than the loop system.
Yes, sir. So, but it will be possible to put a human in a loop, like in such scenarios, right? It not be efficient, but it will be safe.
So this is a standard trade-off between this safety and efficiency.
Yes, sir.
I mean, you can choose to walk and then don't get into the accident.
Yes, sir, definitely. Okay, thank you, sir.
Any other questions? Any questions from online participants? If you have question, you can unmute your mic and you can ask. So, if we don't have any more questions, then we can conclude this session. So, thank you, sir, for your nice presentation. Sir, can you provide the PPTs of your lecture?
Yeah, okay, I'll send.
Okay, thank you, sir. Thank you very much.